So we're going to finish up chapter 5. Won't take long. And then we'll get into chapter 6. And I just have to say at the outset that chapter 6 is one of my favorite chapters. I really enjoy it. I like stereochemistry. I like how things are oriented in space. We'll talk about that quite a bit. But one of the things that we have to finish up in chapter 5 is this idea of alkenes and things that we can add to them. So up to this point, we've talked about adding water across an alkene with an acid catalyst, right? What do I get if I add water across an alkene? What's the new functional group?
Alcohol.
Yeah, we get alcohols. What if I add HX? What's the new functional group?
Alkyl halides.
Alkyl halides. And what can X be in adding HX?
ClBrI.
ClBrI. We can also add X2 if X is what?
ClBr.
Yeah, can't use iodine for that one, right? So we've learned that we can add a lot of things so far across a carbon-carbon double bond or a carbon-carbon triple bond pretty easily. So what I've got up here on the board is oleic acid. Okay, you'll notice that is not a systematic name. That is what we call a common name. How many functional groups are there other than alkane? What are they?
Alcohol and...
Alcohol?
Oh, never mind. One. Yeah, it's
You've
together.
got that one, but what about this? Is that a functional group? Alkene is also a
That's the
functional group,
alkene.
right? Yeah, so we've got an alkene, and what's this one?
Carboxylic acid.
That's right, that's the carboxylic acid. So these are called fatty acids, okay? So your body needs fatty acids. You get these through consumption of oils, things in your diet. This one is called oleic acid, right? How is that carbon-carbon double bond oriented in space? Is it cis or trans?
Cis.
It is cis. It is a cis double bond. And it turns out that cis fatty acids are healthier for you, whereas trans fatty acids are less healthy for you. Okay, and it has to do with their physical properties. Having this cis double bond allows this molecule to be liquid at room temperature, or close to liquid at room temperature. Okay? Now, if I draw stearic acid, what are the differences between oleic acid and stearic acid?
Saturated.
Okay, this is called a saturated fatty acid. Why is it called saturated? It's got the maximum number of hydrogens. That's exactly right. What is similar about the two?
Carboxylic acid.
Okay, they both contain carboxylic acids. What else? If we count the carbons in oleic acid, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How many do we have in stearic acid?
Looks like the same.
It looks like the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the only difference between these two molecules is the saturation. One is saturated, one is unsaturated. So can I convert oleic acid into stearic acid? What would I need to do that? I would need to break the double bond and add something to it. What would I add to it?
Hydrogen.
I would add H2, right?
Yeah.
Well, it turns out that if I take a bottle of oleic acid and I put some hydrogen in with it and I seal it up, and I come back next year and I look at it, it's still oleic acid. If I come back in 100 years, it's still oleic acid. Okay? Hydrogen by itself will not do this chemistry. Now, if I give it 1,000,000 years and I come back, yeah, I'd probably see stearic acid. Okay? But I don't have that kind of time. How do I speed a reaction up? What do I need to speed up a reaction?
Catalyst.
I need some type of catalyst, right? And for these types of reactions, the catalysts are metals. Okay? And you can use any of these metals to do this type of chemistry. There are reasons to select some over others, but we're not going to get into that in this class. So, if you took oleic acid and you put it in the presence of, let's say, palladium, and you bubbled hydrogen gas through it, you would rapidly convert oleic acid into stearic acid. If you go buy partially hydrogenated vegetable oil, this is what they do. They take vegetable oils, they take a catalyst. They usually don't use palladium in that case. It's expensive. And they bubble hydrogen gas through it, and they will reduce, as we say, the double bonds from an alkene and make them into alkanes. We call this catalytic reduction of a pi bond. You will hear me refer to it as catalytic hydrogenation. Okay? Hydrogenation coming from the fact that we're adding hydrogen across the carbon-carbon double bond. Catalytic meaning I need a catalyst. And that catalyst can be palladium, platinum, or nickel. Okay? So they usually take a little bit of fine ground palladium, at least in my lab when we do these reactions. And we do these reactions actually quite a bit. We have what's called palladium black, which is just palladium that has been finely dispersed on charcoal, and we use that for our catalyst. And as you can imagine, platinum and palladium, those are very, very expensive metals, and thankfully they are only needed in catalytic quantity. So we add a very small amount and then blow the hydrogen through the reaction to get this to work. Okay? So how does this work? What's the mechanism? Well, it's complicated. And this is the best that we can do in terms of trying to understand this. And the reason it's complicated is because the metal, as you can imagine, does not dissolve in anything, right? So this is what we call a heterogeneous reaction. Not everything is mixed together. When I put the palladium in with the oleic acid, it just looks like little flakes of palladium floating around, okay? And you have to stir it really well. So it's called heterogeneous. Not everything's in solution together. But if we take this little shiny piece here and we think of that as the metal surface of the palladium, what we know is that palladium will react with hydrogen and it will absorb a lot of hydrogen. So if you take a balloon of hydrogen and you put it on top of a flask that contains palladium, that balloon will look like it's shrinking because the palladium is actually sucking up, if you will, the hydrogen gas out of the atmosphere and putting it onto the metal surface. We also know that alkenes will interact with things like palladium. And so what we propose is that the alkene actually forms bonds to the metal surface just like the hydrogen does. And it's kind of hard to think of that, right? Because we typically only think of hydrogen as forming one bond. And for organic chemistry, that's true. We never draw more than one bond to hydrogen, right? On a hydrocarbon. But this is a little different. This is a metal surface. And so what happens is as the alkene gets close to this absorbed hydrogen, you start to make carbon-hydrogen bonds. So that's what's happening here. One of these hydrogens is transferring to this carbon. And then the other hydrogen on the other side will transfer. And now you get an alkane. And we know that alkanes don't stick to the surface of palladium. They float away. And so it dissociates, as we say, from the metal surface. Well, if you think about this, if I've got a surface, right? And let's say I've got an alkene that's restricted, like cyclic. Would both of the hydrogens be on the same face of the alkene or on opposite faces? If this was the alkene and it was going to come pick up those two hydrogens, would it pick it up on the same face, or would one be on this side, one be on that side? Same face. That's right. And so 100 years ago or longer, they did the experiment, and sure enough, that's what happens. So if you take this cyclic alkene, for example, okay, so we've got two methyl groups attached to the alkene that's part of this 5-membered ring, or cyclopentene ring, right? And we place this in with hydrogen and palladium. What we find is that the product, the two methyl groups, are actually on the same face. They're on the same side. And the hydrogens are on the same side, right? And so as I've drawn this, right, so this carbon atom, this methyl group what does this solid wedge mean? It's coming towards you, right? It's coming, so you've got the plane of the screen, that's where the carbon atom is. This methyl group is coming out of the screen, and where's the hydrogen? It's on the back side of the screen, right? So these are this so-called stereochemistry, which we'll talk about in chapter 6. But these two methyl groups actually happen to be on the same side. And so this reaction mechanism adds hydrogen in what we call a syn, S-Y-N, not S-I-N, but S-Y-N fashion, okay? And so that's an important thing for you all to know. We can also think about, get some other types of information from this catalytic reduction. And so if we think about it, right, we're going to take a weak pi bond and we're going to get strong sigma bonds, right? So should that be favorable or unfavorable? A little favorable or a lot favorable? That's a lot favorable, right? And so these things actually, when you run these reactions, they release heat, right? So the starting materials are here, the products are here. The products are more stable. And so as the reaction happens, heat is released, okay? And so you can get the heat that comes out of hydrogenation, and that can tell us something about the stability of alkenes. So for example, if we look at the example in the book, right, we've got trans-2-butene and we've got cis-2-butene. And up to this point, I told you that the trans double bonds are always more stable than the cis. Well, how did I know that? I know that because if I take trans-2-butene and I hydrogenate it, okay, it gives me let's just call it 116 kilojoules per mole of heat. But if I take the cis-2-butene and I hydrogenate it, I get almost 120 kilojoules per mole of heat, right? So that's more heat coming out. Why is that? It's because the cis double bond is less stable. That means it's higher in energy than the trans double bond. They're both, when you hydrogenate them, they both give you butane, right? They're both the same products. But cis-2-butene is higher in energy than trans-2-butene. And so when they hydrogenate, this one gives you less energy than this one does. Okay, and so we call this calorimetry. You probably did this in 106 with a little coffee cup, right? You can't do this with a coffee cup, but you did coffee cup calorimetry. You understand a little bit about that, right? And so this is how we know that certain double bonds are more stable than other ones. We actually hydrogenated them and determined the amount of heat that they released. And that told us what we wanted to know. Okay? We can also reduce alkynes. What's the difference between an alkene and an alkyne? We've got a triple bond, right? But triple bonds are just pi bonds, right? You've just got a pi bond in one plane and another pi bond in another plane, right? What's the hybridization of these carbon atoms of the carbon-carbon triple bond? SP. What's the hybridization of the carboxylic acid? sp2. Very good. All right. So we can also hydrogenate these, right? What do I need?
Hydrogen and metal.
I need hydrogen and metal, but this time I need more hydrogen, right?
Yeah.
Because I gotta have at least 2 moles of hydrogen for every mole of this. And you can use palladium, you can use platinum, you can use nickel, you can use all the same catalysts that we talked about before. I just happened to put palladium here. Palladium's my favorite metal for this reaction. And it's my favorite metal for this reaction because when I inherited my lab 20 years ago, it had lots of bottles of palladium. And so I use it because it does the job. Okay? Notice we're taking an alkyne to an alkane. Okay, so I can convert an alkene to an alkane, and I can convert an alkyne to an alkane by simply doing catalytic hydrogenation. Now suppose you got a little salty and you thought, hey, maybe I can take my alkyne and I can reduce it to an alkene. Right?
Yeah.
All right, what would I need to do? I got to get rid of the triple bond and make a double bond, right? What would I need to do that?
Hydrogenate it once.
Hydrogenate it once. So Jason suggests that maybe what we do is we take maybe 1 mole of hydrogen instead of 2 moles of hydrogen and do the reaction. Okay? What do you think there? You think it's going to be a nice clean reaction?
No,
Why not?
because it's more favorable for them to go all the way to alkanes.
That's true. What else? Alkenes can also react with hydrogen, right?
Yeah.
They won't just stop here,
Yeah.
right? And do you think that if you just put in 1 mole, how easy do you think it is to just put in 1 mole of hydrogen? It's a gas. It's not very easy to do, right? And it turns out that alkynes and alkenes, although they don't react at the same rate, react at similar rates. So once you form the alkene, it will react again to make an alkane, no matter how much hydrogen you put in, okay? And it will do that until it uses up all of the hydrogen gas, and so it will not go to completion, okay? That's usually what happens. But fortunately, there is a way to do it. And instead of using pure palladium, you use what's called Lindlar's catalyst. You need to know that name, Lindlar's catalyst. I don't expect you to know exactly what Lindlar's catalyst is, but suffice it to say that it is a palladium catalyst that has been poisoned. Okay? Things have been added to it that stop the reaction once you do the first hydrogenation. Okay? And so, since we're going to add the hydrogen in a syn fashion, notice what kind of double bond we get out of this. We get a cis double bond out of this. A very clean cis double bond, meaning that almost all of the molecules that we get are in the cis arrangement here, okay? So if I want to take an alkyne to an alkane, what do I use? An alkyne to an alkane.
Metal,
Okay, metal, like palladium and hydrogen. If I want to take an alkyne to a cis alkene, what do I use? Use hydrogen and
And there's the catalyst.
Lindlar's catalyst.
Could you just explain why you use 2 molecules of hydrogen again?
Well, you've got to have, I've got 2 pi bonds, right? Each pi bond takes 1 mole of hydrogen. So it's just the stoichiometry. So I've added hydrogen across this pi bond, and I have to add hydrogen across that pi bond as well. Yes, ma'am.
You said the Lindlar's catalyst stops what?
It stops at the alkene. You cannot reduce alkenes to alkanes with Lindlar's catalyst. Okay. So they take palladium, they mix it with basically chalk, calcium carbonate, and then they add lead to it. And the lead poisons the catalyst, and it keeps it will not react with alkenes with the lead around. And I'll be honest with you, I'm not exactly sure why that is the case. Although I do know I've used it before and it works very, very well. It's a very nice catalyst for converting alkynes to cis alkenes. Okay?
So, question about that, why would we want to do that? Like, what's it used for?
Well, that's a good question. I'll give you an example. So I had a colleague when I was at Vanderbilt who was studying the oxidation of fatty acids. Okay? And it turns out that it's an important thing to study because atherosclerosis, plaque buildup in heart arteries, right? It's a very important thing to study. And it turns out that fatty acids get oxidized to products that are not soluble and they plaque out in your heart. And so this was about the time that all of this news came out about trans fatty acids being less healthy for you versus cis fatty acids. And so she had to make a whole series of both trans and cis fatty acids, what we call model compounds, to help study this phenomenon. And so she made a bunch of alkynes because alkynes are actually very easy to make. We'll talk about that a little bit more in another chapter. But remember, you can take a terminal alkyne and the hydrogen's acidic, so you can remove it and make a carbanion, if you will. And you can use those to make other carbon-carbon bonds, which we'll talk about, I think it's starting in chapter 7. And so she took those alkynes and made cis alkenes out of them because the fatty acids don't contain an alkyne, they contain an alkene. And so she made these smaller molecules that were easier to study but had the right geometry of the double bond. So that's just one example of why you might want to be able to do this type of chemistry. Okay?
Dr. Masterson,
Yeah.
how do you make the trans alkene?
You can make a transalkene. Your book doesn't talk about it,
Okay.
so I'm not going to cover it.
Oh, okay.
All right? But you can actually convert this from this to a transalkene, but not with Lindlar's catalyst. There's another procedure,
Okay.
and it's not catalytic.
Okay.
But we're just going to focus on the cis-alkene. Does that make sense?
Yes.
All right. Oops. Let's jump into chapter 6. All right. So today we're going to start talking about stereochemistry. When you all hear the word stereo, what do you think?
Radio.
You think of a radio. You listen to it on the stereo. Why do they call it stereo? Pardon? It's because you have two speakers, right?
Oh.
One's over here, and you can hear different sounds based on space. The same kind of thing here in stereochemistry. We're going to talk about how things are situated in terms of space, and we call these things stereoisomers. We're also going to talk about the concept of chirality. That's not chirality, it's chirality. It comes from the Greek word, okay, which means hands. Okay, you have two hands. We're going to talk about that. And we're going to talk about a stereogenic center, which is nothing more than a fancy word for a carbon atom that has 4 different things attached to it. Okay? So, we are going to build some models. Okay, I have got some carbon atoms here. I'm going to hand these out. So, I think one for every table.
Yeah, we can
You all get together. You guys, you three will have to kind of get together, I think, okay? Now, we're all going to build the same thing. Don't build anything yet.
You want to join us? Or I can skip over.
I got 2 more to hand out.
I'll be there.
And I got a new one.
How are you?
Hey, you group?
Just bring the scoot and share over here. Are you
So much work.
All right, now, you all have 1 carbon atom and 4 different colored sticks. All right, now, I don't have exactly those colors, but it's pretty close. I want you at random, get in your groups, and at random attach the different colored sticks to the carbon atom. Do not look at any other group, just randomly pick whatever color and start sticking them together. You'll have to push pretty hard.
Next one. How do you want? Is it not all the cricket?
It might just be like that. Because they're all in all the letters, so it might just look like that.
Now, in your model kits that you all have, you have different colored spheres. You have those colored spheres in there if you've got a model kit. But I don't have exactly those colors in my stick version, okay? What did we make? We made a model. If you were going to name it, what would the parent be?
Yeah, it would be the black one.
Wait. What?
If you were going to name it, what would the parent be?
It would be Trey.
How many carbon? Yeah, it'd be methane parent, right?
Yeah.
So if you were gonna name it with this, you would name it, blue, green, red, white, methane, right? It sounds like we all made the same thing, doesn't it?
Yeah.
I've got a carbon atom that's got a yellow stick, a blue stick, a red stick, and a gray stick attached to it. So if we all made the same thing, I should be able to come around and get every one of our models to line up perfectly, right?
No.
Let's see if that happens.
It doesn't work.
It doesn't work?
Oh, no, it doesn't work.
Notice I can get the
Two.
blue, the carbon, and the grays to match up, but I can't get the other two on his.
Yeah.
So this, mine, is clearly different from his, right? All right, keep track of it for me. So one that's different. Now let's take a look at yours.
Is that the same thing?
Two that's different. You all have the same one. Very good. Let's see.
You good? Good.
Same or different? Different.
This is a good half.
Well, goodness gracious, we're all making different. You all didn't do this at random. Let's see. How about yours? No matter what I do, I can't get ours to line up either, can I? See how I broke my experiment. Y'all didn't do this at random. Interesting. Usually when I do this in a class, we end up with a 50-50 mix.
Oh.
And now we're at 0.
And now I'm the only one that built one. Y'all built them the same way, y'all connected them in the same order, which is odd, okay? But it still shows the point, right? You all have something different from mine. How would I name this? I would still name this blue, green, red, white, methane. But clearly they're not the same. Mine is one type. Yours is a different type. Mine is one hand version, yours is the other hand version, okay? These are said to be chiral, okay? If I take your model, wait, I must have picked up somebody else's model.
I think so.
Let's see that. Somebody's got mine. Yeah, somebody got mine. I must have swapped something. Where did I swap? There it is. Notice how this one, which is my original, if I set them there, do they look the same?
It's mirrored.
It is a mirror, isn't it? This is like looking in a mirror. This is what happens when you hold your left hand up in a mirror.
Looks like
Your right hand stares back at it, doesn't it? These are mirror images of one another. So if you think of this being a mirror, this is reflected to here, this is reflected to there, so on and so forth. They are mirror images of one another, but they are not superimposable on one another. Just like my hands. They are mirror images, but my right hand is not my left hand. Okay? My right hand is not my left. You all know that intuitively, right?
Yeah.
Right? If you go get a baseball glove and you try to put your right hand into a left-handed glove, what happens? It doesn't work. It doesn't work at all, right? And so molecules can also have this so-called chirality or handedness to them. One is like a right-handed molecule, one is like a left-handed molecule. Okay, and that's what we're going to talk about today. And it turns out that this handedness is extremely important. Okay? Extremely important. You all need to know about this because it can be a matter of life and death, actually. If your doctor gives you the wrong hand of a medicine, you could die. Okay? If a chemist doesn't make the right hand, the correct hand, I should say, of a molecule, you can die. It's important to know this kind of stuff. So how things are attached in 3 dimensions is extremely important. Okay? And so we've talked about isomers a little bit already, right? We talked about cis and trans isomers. Those things have different things pointing in different directions, but they're not chiral. You have to have a carbon atom with 4 different things attached to it to be chiral. Okay? We call that a stereogenic center. Okay? And so we've learned about constitutional isomers, right? These 2 things have exactly the same number of carbons, hydrogens, and oxygens, but they're connected differently. This is an alcohol functional group. This is an ether functional group. We'll learn about ethers later. Don't worry too much about it. Stereoisomers, however, are isomers that have the same connectedness. And there are 2 flavors of them. There are enantiomers, which is what we're making. When you have a non-superimposable mirror image of something, that is called an enantiomer. So this and this are enantiomers of one another. Okay? Diastereomers have the same connectivity, but they're not mirror images of one another. Notice the cis 1,2 dimethyl cyclohexane and the trans 1,2 dimethyl cyclohexane. All the atoms are connected the same, but they're pointing in different directions in space. These are not mirror images. If I hold this, I hate that. If I hold this up to a mirror, I do not get that. Okay? Can everybody see that? And in fact, you would have different names, wouldn't you?
Yeah.
One would be cis 1,2, the other one would be trans 1,2, right? So those are diastereomers. But my favorite area of conversation is in enantiomers. This is what my research group does. We make single-handed molecules, if you will. Okay? It turns out that single-handed molecules are difficult to make. And it turns out that that's why a lot of your medicines are as expensive as they are. Because it takes a lot of effort to make a single hand of a molecule. Okay? We'll talk a little bit about that. Okay?
What do you when you say make a single hand of a molecule?
Well, if the experiment had gone right, we all would have made a random sample and we would have found that 50% of the molecules that were made would have been the one that I made and the other 50% would have been the other one. Okay? But that didn't work out for whatever reason in our little experiment here. Somehow you all got together and made the same thing, which is unusual. And anytime you have a 50-50 mix of those 2 things, we call that a racemic mixture. Okay? And so you have a mixture of both hands. But in my lab, we try to make only one hand, and leave the other one out of the reaction. Okay? And that becomes difficult. But you also will find this type of stereochemistry stuff in molecules that you all are familiar with. So for example, I think you all will recognize that these rings are nothing more than glucose linked together to form complex carbohydrates. Okay? This is cellulose. Notice that the cellulose linkages, right? It's an equatorial and an equatorial that links the 2 glucose molecules together. But notice in starch, it's an axial bond and an equatorial bond. They're different in 3 dimensions. So what's the difference, for those of you who are in nutrition, what's the difference between cellulose and starch?
You can't digest cellulose.
You cannot digest cellulose, right? You eat salad just passes through as roughage, right? We call it fiber, right? It can't be digested by the human digestive system. What about starch? Can be, right? We eat bread, right? But they are nothing more than stereoisomers of one another. Cellulose and starch have exactly the same number of carbons, hydrogens, and oxygens. They are connected in the same way, except one uses all equatorial bonds to link the two sugars together. One uses an axial and an equatorial bond to connect the two sugars together. Can't digest? Can digest, right? And it turns out that this makes a very big difference in how these things interact with one another. Cellulose, when you look at it, if you look at a big polymer of it, makes these sheet-like structures, whereas starch makes this helical structure. Okay? All because of just one little difference in a bond. Okay? And of course, this means that I can eat starch, right? I get it from wheat, I eat bread, I get energy, but I can't eat cotton. Right? I mean, I can eat cotton, but it's not going to be good. Right? Right? I mean, I guess I could chew on a piece of cotton, but I'm not going to get any energy out of it, right? But the good news is, right, because of this bond, I can make my clothes out of cotton and I can wash them. And I can dry them, and I can wear them again, and wear them again until they wear out. Would I make my clothes out of starch?
No.
What would happen? It would wash away, right? Right? Have you all ever seen those packing peanuts that you throw in the sink and wash down the sink? They're made out of starch, right? They're not made out of cellulose. Okay? They have different properties because of this bond. Okay? So there are two main classes of isomers. There are constitutional isomers, which we've talked a little bit about, and there are stereoisomers. Okay? Anytime you see IUPAC, I don't think the book uses that terminology. IUPAC is an organization that comes up with the rules for naming stuff. Okay, so just think systematic names. Okay, so constitutional isomers, of course, same number of atoms, but they're going to be connected differently. You might have the same functional group, you might have a different functional group. Stereoisomers, however, will always have the same functional group. Okay, so on an exam, if I gave you which of the following are constitutional isomers, look for different functional groups, look for different connectivity. If I ask you which of the following are stereoisomers, and two things don't have the same functional group, they can't be stereoisomers. Okay? And we call a particular three-dimensional arrangement of atoms a configuration. So this has the right-handed configuration. Yours has the left-handed configuration. Okay? How in the world do we distinguish between right and left hands with molecules? I'm going to teach you that as well today. Okay? It's not hard, but there are rules associated with it. Cool.
You said on, like, your example said if you were asking on an exam for the constitutional isomer, look for different functional groups?
Yeah, so if you have the same number of carbons, hydrogens, oxygens, whatever, the same number of atoms, types and a number of atoms, but you have different functional groups, they have to be constitutional isomers of one another.
Right, why, so why up there, what does it mean by saying the same or different functional groups?
Well, I can give, well, for example, the example right here. Both of these have the same functional group, right, but they're not enantiomers. These are constitutional isomers because they have different functional groups, right? But I can also make another alcohol of this that would also be a constitutional isomer. Right? So even though those have different functional groups, I can draw one more. Can anybody tell me what it is? So it's got 3 carbons, right? No, wait, 4 carbons. And an OH. Right? So there's that one, which is up there. There's also that one. And then there's the seagull one, right? It's a bat? All right. Looks like a bat. If we put the lone pairs on, it would really look like a bat, wouldn't it? There you go. All of those molecules have exactly the same number of carbons, hydrogens, and oxygens. Okay? but they're connected differently. They are constitutional isomers. But this has the same functional group. These have different functional groups. But if I gave you just those, you would know those have to be constitutional isomers because the functional groups are different.
But stereoisomers always have to have the same, right?
Yep. For example, these two right here, exactly the same functional group, but you'll see that one is a mirror image of the other. Okay. We'll talk a little bit more about that. All right. So, get in your groups and practice this. Answer those three questions. Classify each of those pairs as constitutional isomer or stereoisomer.
Stereo means different.
What means different?
Stereo means different, right?
No,
For right now.
Not really. Constitutional is more different than stereoism. Constitutional means it's connected differently, whereas stereoism is just position. So,
That one's traditional.
the first one's constitutional.
No.
Yeah, I agree with you.
How things are oriented in three dimensions.
Third one
Stereo.
is stereo.
What's the second one?
Stereo.
You think the second one is stereo? Yeah.
And the other one is
I don't think the second one is stereo, yeah. Look at that thing. Like it's, you know, the left one, like they're very different. The left one is like a square.
So it's constitutional.
It is constitutional because just the position of the oxygen, like. So on the right one, the oxygen is connected to one carbon and one hydrogen. And on the left one, on the square one, is connected to two carbons. So it's definitely different. Does that make sense? Okay.
And the third one would be
Third one, you're right.
All right, how about the green pair? Are they constitutional stereo?
Constitutional.
All right, I heard constitutional and I heard stereo. What's the functional group in both of them?
It's just odd names.
It's just alkanes, right? Okay, so they have the same functional group. So they could be, based on that, maybe they're stereo.
Maybe.
But are they connected the same?
Now, the location of the substituents.
Okay, so let's look at the first one. What's the parent?
Pentane.
So this is going to be a pentane parent. Okay, and what are my substituents? Two methyls, and where are they located?
2,3-dimethyl.
Okay, so this is 2,3 hyphen dimethyl pentane. Now let's look at the other one. What's the parent here?
Still pentane.
Still pentane. So it's a pentane parent. What are the substituents?
2,4-dimethyl.
2,4-dimethyl, right? Constitutional isomers cannot share the same name. Okay? And so doing this, I can realize, look, it's the same number of carbons, same number of hydrogens, different names. They have to be connected differently, right? The methyls are on 2 and 3 here. Here they are on 2 and 4. So they are constitutional isomers of one another. How about the blue pair? Those are also constitutional. They are. They're also constitutional. That one's a little easier to see probably, right?
Yeah.
One looks like a box, one looks like a triangle. But when you add up all of the carbons, hydrogens, and oxygens, you'll see that it's the same. And so they are constitutional isomers. What's the functional group?
Alcohol.
Alcohol. What's the functional group?
Ether.
Ether. That's right. So ethers and alcohols are quite common in terms of constitutional isomers. How about the yellow pair?
Stereo.
Those are stereoisomers. Notice one of the methyl groups is coming out of the plane of the board. One of them is going behind the plane of the board. On the other one, both of them are coming out of the plane of the board. This and this are not mirror images of one another. You cannot hold any one of these up to a mirror and get the other one. Okay? You all won't admit to it, but I know some of you are going to go home and build something and hold it up to a mirror and see if I'm actually right. Okay? It's okay. You know you will. All right. So, as we've already mentioned, chiral molecules are non-superimposable mirror images. Okay? My left hand is a mirror image of my right hand. Ignoring my little blemishes and stuff, right? But I can't take my right hand and make it my left hand. Same thing with the molecule that we built, okay? We call this handedness, okay? Everything, of course, has a mirror image. But that doesn't mean that everything is a non-superimposable mirror image, okay? For example, when you go to put on your socks in the morning, do you worry about right-handed or left-handed or right-footed or left-footed socks?
No.
Not unless you have the funky ones with the toes broken, right?
No,
Somebody
it's
may
different
have.
sometimes.
Huh?
Nike ones have a left and a right, and it makes a difference.
But just a regular tube sock. Doesn't matter. Doesn't matter. You don't sit and look at it, which one's mine. But you do think about your shoes, don't you? Which one's left and which one's right. Yeah. And it turns out if you take your socks, you will find if you hold up one of the socks, you'll get the mirror image, and you hold that one up, you get the same mirror image, and you can just superimpose them. You can take one sock and lay it perfectly on the other. Socks are what we say are achiral, okay? They do have mirror images, but those mirror images are superimposable. I take my left sock, if you will, and I can lay it perfectly on my right sock. Okay? But I can't take my right boot and put it on my left foot.
Yeah.
Doesn't work that way. Okay? So are my feet chiral? My
Yeah.
feet are chiral,
Yeah.
right? My hands are chiral. We just chose to call it handedness instead of footedness. Just sounds better. It comes from the Greek word. Chair or something like that. Now, let's take our model. I don't know if I have enough pieces. You all will know. Might have to share one. Now, we just established that having a carbon atom with 4 different colored spheres around it, or 4 different things, makes it chiral. What happens when we leave our, let's just call gray white, and red, of course, is red, and let's replace the yellow with a blue. I think you all will agree that we now have 2 of the same thing on a carbon atom, right? 2 blues. We now have all the exact same thing.
Oh.
Even though, notice that's a mirror image,
Get to superimpose it?
but I can perfectly superimpose it.
Oh.
It's a mirror image that is perfectly superimposable. And that will be the case for each and every one of us.
So you're saying if there are 2 substituents that are the same, then they would be achiral?
If you have 2 or more substituents that are identical, it can't be chiral. Yeah? Yep. Yep, we all have the same thing. So anytime you see a carbon atom that has like 2 hydrogens attached to it, it can't be a chiral carbon atom.
Okay.
It cannot be a stereogenic center. Okay? you have to have a carbon atom with 4 different things attached to it. Okay? Once you break that rule, it is no longer a chiral molecule. Okay? Now, here's a few things you need to memorize. And are there some exceptions to some of this? Yes, and we're not going to get into them in this class. Okay? But in general, a molecule that has no stereogenic centers will not be chiral. What is a stereogenic center?
Have 4 different.
A carbon atom with 4 different substituents. So if you don't have that, for the purposes of this class, it's not going to be chiral. Okay? If you have a molecule that has 1 and only 1 stereogenic center, it must be chiral.
So stereogenic center means 4 different molecules. attached.
4 different things attached to a carbon atom. So that's what, well, we don't have
Has
that
to be
now.
carbon?
For the purposes of this course, yes. Can it be other atoms? Sure. Okay, so we've got 4 different things attached to this carbon atom. I've only got 1 stereogenic center. This must be chiral. Okay? If, however, I have a molecule that has 2 or more stereogenic centers, the molecule may or may not be chiral. Things get a little more complicated when you have more than 1 stereogenic center. And achiral molecules contain a plane of symmetry. But chiral molecules do not. We'll see some examples here in just a moment.
So if it has more than 1 stereogenic center, it might not be. So it could be either.
It could be either. Yep. A plane of symmetry is a mirror plane that cuts the molecule in half somewhere. Okay? So if we look at what we just made, the dyed blue, red, white methane, where is there a plane of symmetry?
Yes, it's this one.
Right through here.
Yeah.
Goes right through the white, the carbon, and the red stick, and then the 2 blue sticks are, so it has what we call mirror symmetry. Think about it, since there's mirror symmetry in the molecule, if I hold it up to a mirror, it gives me back exactly the same thing. When I hold this up to a mirror, I get exactly this in my mirror image. Okay? Because it already contains a mirror plane of symmetry.
So all achiral molecules do have a plane of symmetry.
That's right. Okay. So for example, right, if we used bromochloromethane, you can see that mirror plane of symmetry. The bromo is the red sphere, the green is the chlorine, the 2 whites are the hydrogens. Notice this carbon atom has 2 of the same group. It can't be chiral. And because it has 2 of the same group, it has a mirror plane of symmetry that's shown right there. Okay? However, if I replace one of those hydrogens with a fluorine, and I have bromochlorofluoromethane, notice there is no plane of symmetry anymore. Right? And so this is a chiral molecule. This is a carbon atom with 4 different colored spheres around it. It's different. Right? No plane of symmetry. So we can go from achiral to chiral by simply replacing an atom. Okay? If you do not have a model kit, I'm sorry that it wasn't put down as the required materials when they put the book order together. I don't know why Dr. Hayhurst chose not to have you all buy one. But if you can't afford one, I highly recommend you go to Walmart and buy a bag of colored marshmallows. And toothpicks. You can do the same thing with marshmallows and toothpicks. And the nice thing about marshmallows and toothpicks is that
Eat it
you
after
can eat
you
it.
make it.
Huh?
Eat it after you make it.
You can eat it after you make it. That's right. So here's an example of a molecule. This is called 2-butanol. Okay? So it's an alcohol. And I think you all will agree that this carbon atom is the stereogenic carbon. It's got a methyl group attached to it, an ethyl group attached to it, a hydrogen, and an OH. 4 different things around that stereogenic center, right?
Yeah.
And I can draw it where the carbon atoms are all in the plane of the board. And I can draw a solid wedge coming out of the plane of the board and put my OH there. And I can draw this dash wedge, which means the group is going behind the plane of the board, and I can put my hydrogen there. There are many ways to draw it. This is the simplest. And now I can draw the mirror image of that. So if I imagine a mirror plane being here, right? So OH, mirror, reflection, OH, carbon, reflection, carbon, methyl, reflection, methyl, hydrogen, right? This is the mirror image, right? These are non-superimposable of one another. One is right-handed, one is left-handed. They are enantiomers of each other, okay? They're non-superimposable mirror images. We can also have chiral centers that are part of a ring, okay? So for example, this is called an epoxide. It's a different functional group. It looks like an ether. Don't worry about the functional group yet. But where is the chiral center in that molecule?
The C and the CH.
So oxygen, does it have 4 different things around it?
No.
Oh, no.
No.
No, that's okay. It's all right. Where's the chiral center?
The first C in the CH3.
Right here?
I think so.
Okay. So let's figure out if that's true, right? Clearly, it has a hydrogen and a methyl group attached to it. Those are 2 different things, right?
Uh-huh.
Is this different than this? Yeah,
Yeah.
right? So we have, obviously we have hydrogen attached. We have the CH3. We have the OCH2. And we have the CH2O. Those are 4 different things around that carbon atom, okay? So that molecule is chiral. It has 1 chiral center. Why can't this be a chiral center?
It has 2 hydrogens.
2 hydrogens attached to it, right. So CH3 obviously can't be chiral because it has 3 hydrogens attached to it. And so there's only 1 chiral center. So this molecule must be chiral, okay? Now I told you that this matters. And that you really need to know this for a couple of reasons. Let's talk about biology for just a moment. So
Lovely.
about 50 years ago maybe, or so, maybe even a little longer than that, you know, pregnant women had to suffer through morning sickness. It wasn't pleasant, right? I can't imagine what that would be like, right? And so what they did was they gave pregnant women this anti-nausea drug called thalidomide. Okay? It has 1 chiral center right there. That carbon has this carbonyl attached to it. This CH2 attached to it, just happens to be part of a ring. It has a hydrogen and it has this nitrogen. I think you all will agree that that's 4 different things. And so it has 1 chiral center. Okay? This mirror image, or this image of it, this hand, if you will, we'll call it the left hand, actually treats nausea very, very well. It keeps women from getting sick in the morning and having morning sickness. However, the non-superimposable mirror image of this is a teratogen. Does anybody know what that is? It causes severe and gruesome birth defects.
Oh.
So they were noticing that women who were on thalidomide had this high incidence of premature births, births with missing limbs, partial pieces of the skull missing. It was horrible, okay? It is the same molecule, but different hands. And they gave this to females as a racemic mixture. 50-50. They had a 50-50 mix of both the right or the left hand and the right-handed molecule. The left hand did what they thought it would do. The right hand caused harm to the unborn fetus. Okay?
And so did they not know that they were different, that there were a right and a left hand in
They knew that there was a right and a left hand, but this was long before we really understood the implications of chirality on biology. okay? And so, what might be a solution? Making only the left-handed one, right? And they tried that. And it turns out that it did treat nausea, but it still caused birth defects. Because your body has a mechanism, at least for this particular molecule, that can convert this molecule into that molecule. So we no longer prescribe thalidomide to women who are pregnant to treat nausea. There's just no way to treat it with this particular drug. There are other drugs on the market that do that now, but this was a horrible case in medical history.
It sounds downright terrible.
It was terrible. It was absolutely terrible. Okay? Now, if you think about other molecules that you might be familiar with, everybody likes a little sugar every now and then, a little table sugar. Sucrose. Look at all the chiral centers in sucrose. Every one of these carbon atoms that has a star has 4 different things attached to it. Mother Nature makes only that particular stereoisomer that we call sucrose. Okay? Doesn't make any of the others. It's very good at making only the one enantiomer of sucrose. In fact, if you change any one of these chiral centers into the other configuration, it's no longer sweet.
Oh.
Is stereogenic center and chiral interchangeable?
Yep.
words?
Stereogenic center and chiral carbon are the same thing. Yep.
Wait, stereogenic?
Stereogenic center and chiral carbon, for the purposes of this class, mean exactly the same thing. Okay? Taxol. This is one of the most potent anti-cancer agents on the market. Look at all of these stereogenic centers, all those things that are marked with a star. To treat just a handful of people with breast cancer with Taxol would have decimated the forest that this came from. This is a natural product that comes from the yew tree. It comes from the bark of the yew tree. You would have had to completely decimated the forest to treat people. Okay? We had to find a way to make that. And we had to make it where each and every one of those chiral centers is exactly the right orientation. That's tough. It took 20 years for people to figure out how to do that. Okay? Took a long time. Okay?
Even if people figure it out, does it, remember how you said that, like with that other thing, it changed in the body even when they made it just so what if the same thing happens? How do you know that?
They now that we know that, we test for that. We see whether or not there are mechanisms by which one enantiomer can be converted to the other in a biological system. I'm getting off a little topic here, but one of the reasons, again, why your drugs are so expensive is because the Food and Drug Administration mandates that if you have a chiral molecule as a drug, you have to show which enantiomer does benefits. And if you want to prescribe that drug as a racemic mixture, that is both of them, you have to show that the other enantiomer causes no harm. How easy is it to prove that something causes no harm?
Not easy.
Not easy at all. Proving a negative is almost impossible, right? So drug manufacturers make only the enantiomer that they know is active and try to prescribe that, only that enantiomer, unless they are confident that the other enantiomer causes no harm. Okay? And there are some drugs that you take as racemic mixtures. We'll talk about those as well. But, you know,
So why would
that's a
you
tough
do that?
Why would you do what?
Why would you make it a mixture?
It's cheaper.
Yeah.
Yeah. I mean, it's just randomly putting things around the carbon atom. Very easy to do. But then if I told Jason, I need you to put everything on exactly like I did, he would have to pay attention to how I'm putting things on in space and how things are pointing. And that's what chemists have to do. And it gets tough. There are lots and lots of Nobel Prizes for people that have figured out how to make stereogenic carbons. It's that important. Okay? There are more Nobel Prizes awarded to organic chemists than any other scientist because of this difficulty. Okay? Being able to make stereogenic centers. Okay? Now, up to this point, we have been talking about this mirror image, that mirror image, right, left, right? But that's not very descriptive. Right-handed, how does, I mean, if you really think about it, how does that really look like a right hand?
Doesn't.
It doesn't. I couldn't tell Jason to go take these sticks and make it look right-handed. We have to have a nomenclature, okay? And we use what's called the R or S nomenclature, okay? So, we need to be able to distinguish them by name. R, 2-butanol. S, 2-butanol. Instead of right-handed 2-butanol and left-handed 2-butanol. If I told Jason, go make the R enantiomer of 2-butanol, once he knows the rules, he would be able to draw that out for me. He would be able to do that because it's systematic, okay? We use what's called the Kohn-Ingold-Prelog system to determine R and S. And you've all been, so far, you just haven't known it yet, but you have been introduced to the Kohn-Ingold-Prelog system. I call this the CIP system because I don't like saying Kohn-Ingold-Prelog over and over again, okay? But basically what you do is when you find the carbon atom that is the stereogenic center, you assign priorities to the groups on that carbon. You all did this in determining cis and trans,
Easy.
E and Z, right? So you already know how to assign priorities. We're going to start by assigning priorities based on atomic number, where they sit on the periodic table. So if I look at my bromochlorofluoromethane, right, I know that bromine has the highest atomic number, chlorine has the next highest atomic number, fluorine has the third highest atomic number, and hydrogen will always have the lowest atomic number, right? It's number 1 on the periodic table. And so we assign these priorities based on golf scores. Golf. Lowest wins, right? Not highest.
Well, are we talking about the same golf, Tiger Woods golf, or just golf in general?
Golf, right? We want the lowest score in golf,
Yeah.
right? So the lowest number is the highest priority, right? So 1 is always assigned the highest priority. Don't get that confused. Some people think 4 is greater than 1, so 4 is better. That's not true here, okay? All right. So the rule is if you assign the highest priority based on atoms, right? But what if the 2 atoms are the same? In this case, for 2-butanol, I've got hydrogen, which is going to be obviously number 4. I've got an oxygen, which is obviously going to be number 1. And I've got 2 carbons. Now what do? What do we do in E and Z?
The lumbar carbon chain.
We look at the next atom, right? So this carbon is attached to what?
Hydrogen.
3 hydrogens, right? What is this carbon attached to?
2
Two
hydrogens
hydrogens
and
and
a
a
carbon.
carbon.
It's attached to a carbon and 2 hydrogens. So which one takes priority?
That one.
The right one.
Right, so this is going to be 1, this is going to be 2, this is going to be 3, and this is going to be 4. Okay? And so that's how we're going to determine the priorities. The same way we did for E and Z. Nothing new there. All right? And so in 2-butanol, I've got them drawn here. We've got enantiomer A and enantiomer B. You can call one left and one right for right now. And I know that my OH is going to be my highest priority. My CH2, CH3 is going to be the second priority. My CH3 is going to be the third priority. And my fourth priority is going to be hydrogen, or my lowest priority. Okay? You've got to do that each and every time, systematically. Then what you have to do, and this is where model building comes in handy. And I always use the gray or the white sphere as hydrogen, okay? That's going to be my lowest priority group, right? You always grab your lowest priority group and you turn it away from it. And you look down the carbon lowest priority bond. Just like that. Okay? And if your priorities go 1, 2, 3, think of that as turning your car to the right. We call that R. R is to the right. It's easy to remember. But if it was 1, 2, 3, and it was the other way, we call that S.
So it's clockwise and counterclockwise.
Clockwise, like I'm turning my car wheel to the right,
Right.
that's R. If you remember that, you know the other one has to be
Okay.
S. Okay? Very, very important. You have to have that lowest priority group away from you for this to work. Okay? How many people have ever seen a picture of Big Ben? What is Big Ben?
The clock power and longitude?
It's a clock. Now, if you're outside Big Bend and you're watching the hands move and you've got all day to watch, which way do the hands move?
Clockwise.
They move clockwise, hence it's a clock, right? But you take a tour and you go up inside Big Bend and you watch the hands, which way do they look like they're moving?
You gotta remember that.
Are you getting younger?
No.
Of course not. You're looking at it wrong. And the same thing with a model. So if I have the lowest priority group facing me, if it looks like it's going right, it's really going left.
Ah.
The lowest priority group must be away from you. This is why model building is so important. I could draw it on a piece of paper to where the lowest priority group is facing you. You would have to build that model, turn it, and look at it. Now, I can look at these things on paper, and I can do it pretty well in my head. You can't. Some of you might be able to. Some of you, but most can't. And that took me, I was well into graduate school before I could do that.
So you take the lowest priority and you turn away from you, and then what are you looking for, like, the other priorities?
Yep.
What if it's like 1, 4, 2?
4 is always going to be away from you. So let's say it's 1, 2, 3, that's to the right.
Okay, what if it's 1, 3, 2?
If it's 1, 3, 2, then it would be 1, 2, 3. Right? 1, 2, 3. You go 1, 2, 3. Then that would be S.
Oh.
Okay.
Yep. All right, we're going to pick up with this on Wednesday. We are done with 5, so you can bet we're going to have a quiz on 5 on Wednesday. All right? On your way out, please leave your model kits for me and put your exam redos where Selena was sitting.
How long does it take for this one?
Two days. Just make sure you tell them one, because they sent me one batch. They sent me 2.
Oh.
Yeah, so specify how many you need, because they sent me 2. And I sent one back. Back.
So you're going to have proposed adding water across both of those carbon-carbon double bonds.
Yes.
I'll have to look at it.
Like my initial guess was this.
Well, remember, you can add water on either from the top or from the bottom, on either side of the pi bond, right? So you can think about OH coming out or OH going back. So that's how you need to think about
Okay, so it's like, and like up and down.
that. Right, so if I'm adding water across this, I can add the hydrogen here and the OH coming up, or I can have the OH going down, right? And I can do the same thing here.
So it would be like this, or
Take care, sir.
that.
What was that? Take care.
And I can do that here, and you can do that here, although it's not as important here. But this group is gonna be equatorial, if you drew this out in a chair. Okay, because big groups are always equatorial, right? So then how the OH, if the OH is on the same side as this group, then it would be like cis, and if the OH is on the opposite side of this group, it would be trans.
That was a lot.
You gotta build it out, one step at a time, so draw the mechanism. Let's see if that helps, okay?
I'm sorry, can you walk me through it again?
So, right?
Yeah. And then it wants us to draw a mechanism, like, you want us to break it down part by part. Or just,
Water and acid, right?
Yeah.
So I can get, right?
Yeah, that's what I drew.
Yep, and so
don't know why are we doing that?
Well, I'm drawing it as a chair,
Why?
so you, because you, it asks about cis and trans, right?
Yeah.
So you gotta know.
Do
so
we
I
have to
can-
draw it as a chair when we need to know if it's cis or trans?
Well, you gotta know where the groups are, right? And I know this is a big group, so it's gonna be equatorial. And then I can have a molecule where the methyl is equatorial and my hydrogen, or my oxygen is axial, or I can draw it. The opposite.
So this is equatorial and this is axial? Those
This-
both look equatorial.
This group, this is a group, and it is equatorial.
Oh,
So this is equatorial, this is equatorial, this is equatorial, this is axial.
okay. So this would be trans?
And if I flatten it out, this and this would be on the same side, so this would be, these would be cis to one another here. And if, and this and this one would be cis to one another. Right? But I can say that the methyl is cis, but the methyl here is trans.
Okay, would we
This
get
is-
a question this complicated on a test? I feel like this is, I feel like we didn't do this in class.
We didn't.
We did or we didn't?
We didn't do anything this complicated.
Okay, like, it's really confusing me, like, are we gonna have to know how to do something like this on? Okay. So do you want me to try and work it out?
Yeah, look through it.
Can I see a picture of this?
Yeah.
But we're not gonna be getting something like this, because this is just confusing, like, it's a lot of steps in one
Okay.
question.
It is a lot of steps. Part of it is to show that things can be accomplished.
I actually have a question on this. So I'm able to stay here and I put E instead of E and there's no E. And I was just wondering, like, is there any way I can get that for me or is it just? Okay. Okay, that's fine. I just figured it was worth asking.
Yeah, no, well, that's.
Thank you.
Yeah, just relax.